Once again, here we are. This is the fourth video lecture. Physics 105A, video lecture 4. So let's get started. I'm going to start with an announcement about the homework I put up last time. So homework tip, we had F of R equals B K hat cross R divided by R to the N. And we were just looking at the X and Y component. So we're defining it like that. And the tip is, and we wanted to take the curl of this thing. It's going to have an interesting result because there will be a value of n for which the curl vanishes, even though this is intrinsically something that has a curl. But just make sure you first, I forgot to mention this, write it out. It'll have a 0k component. And then, so put in what these two things are, and that's the vector whose curl you're taking. Okay, so then curl of that equals. Okay, so I just wanted to bring that up to make sure everybody doesn't try to take the curl of it in this form. You could actually take the curl of it in this form. You need some of those formulas from vector analysis. But go ahead and write it out what it is as it's component-wise, and then go ahead and work on it. Okay, so now let's get to the matter at hand. We are looking at Newton's law for what? For this case, functions that are purely forces that are purely a function of position. And we had gotten to the discussion of the central force. So when F of R has this form here, this is just the unit vector. I could also call it R hat. I may do that interchangeably. So when the force has this form right here, then it's what we call a central force. Right? It's a special case of this one right here. It's definitely going to have a potential energy because we showed that the potential energy exists for this type of force right here. So yeah, this is a central force. I'll put the examples up that we're interested in right away and say a little bit about them. We could have F equals minus G product of two masses over R squared, and there's the vector nature of it. Yeah, that would be Newton's law of universal gravitation. And since this is outwardly directed, the minus sign is what's telling us that we have an attractive force. So Newton, I'll just call this Newton gravity. So that's our major goal here. We could have F equals minus K Q1 Q2 over R squared. Same unit vector, and that would be Coulomb's law for electrostatic attraction of charged particles. Now Coulomb's law actually doesn't need the minus sign. Let's erase the minus sign because of course we have like charges repelling and unlike charges, which would then have one of them has a minus sign, would give us the minus sign intrinsically. Okay, so that would be Coulomb's law. All two of these, both of these, we're going to consider in the form F equals minus alpha over r squared times that unit vector. Okay, we're just going to consider the general case. I'll put a note right after Newton gravity. The two-body problem, right? That's our main goal in this semester, the two-body problem, Kepler problem. Two-body problem reduces to star here. It reduces to a one-body problem, right? There are two bodies in this problem. We've been doing a one-body problem. Two-body problem reduces to this. I can show you that anytime. I'll show it to you later. It's interesting in its own right, and actually essential to the whole arguments. Good, so that note goes with here. So we're looking at this, and since I don't have room underneath here, I'll erase, but you guys just continue this list as though it were all up here. So the other example that I want to look at here is F equals minus K times R. So what is that? That looks like a Hooke's law, and it really is. It's a three-dimensional Hooke's law. Hooke's law in 3 dimensions, and we can write minus K R. We multiply and divide it by this magnitude R right here. Doing that because then we see that that is our F of R. Okay. So this would be, I'll put a note here, this is the three-dimensional harmonic oscillator. Okay. We don't know that it's a harmonic oscillator, do we? Let's say three-dimensional Hooke's law. That harmonic oscillator business will come about soon enough. Good. And I'll immediately formulate a little bit of homework for us. So putting this one underneath here, F equals minus KR, R divided by R. The point is, next is to find the potential energy. Okay. Homework. And these are trivial. I always do them in the lecture, but I'm just going to post the best of both worlds. I'll write down the answer. You guys will do it. It's a trivial calculation. Calculate U of R equals minus alpha over R for 1 year equals K over 2R squared for the second one. Continuing on, using U of R equals minus integral dot dr A to R for problem 1, A goes to infinity. 2, choose A equals 0. Okay. Good, I got that out of the way. Those are very easy to do, and you can practically just eyeball them. But I'm going to continue with the discussion of the potential energy now. Okay. So let me just erase the whole thing and get started over. But yeah, you guys will calculate these two, leave room in your notes, just fit them in where they belong, and then turn them in as well. Remember, you're gonna take pictures of your home and turn them in as well. So these are on next week's homework, just to get something for today's lecture. Yeah. So let's start this development now that we've written these things down. This development that I'm about to present is one of the most interesting in mechanics, really. So let's see where we are once again. Taking it from the top, we have Newton's law, because I want to do this systematically now. Or the central force. So for the central force, this is what we have. And we had U of R equals minus integral F, I'll just write it in symbolic form here, F R A R, and energy is conserved. That's how far we have gotten. In other words, this is a real potential energy. Its gradient gives us the force. The gradient of this gives us the force. We'll get to that explicitly again. So, what we're going to do now is plug this into here and investigate it a bit. Because you notice this is U of vector R, and that's going to change a little bit. So now, U of R equals, let's plug in this definition, F of R, unit vector R dot dr. And we'll take a look at this before we continue on with our result. So this is a scalar product. We'll just literally see what it means. It is the magnitude of the unit vector times the magnitude of dr times the cosine of the angle between them. And in order to have a picture, I'm going to use this corner of the board. This should work. So here's our central origin, and we've got some path, and we've got some path here from A to R. It's a little long here. But what is our central force thing? Is that the force is along this straight line here. I may have to redo this with a bigger picture, but let's see how this one works. Now I'm just taking the point where we cross this path here. This is exemplary. Here's my dr. And here's my R over R central vector, okay? That's the point. So you can see there's a little angle between these. And if we calculate this, okay, you guys can do a bigger picture of this. I think it's clear what I'm driving at. I hope it is. So if we calculate this or just investigate it, what do we have here? We have a 1, and then the dr cos theta, it's the projection of this dr vector onto the radial direction. So that is just dr in radial direction. So yeah, make a bigger picture of this idea, but what this gives us is F of R PR from A, which is the magnitude of this one, you can think of concentric spheres at this point, to R, which is the radial distance out from that central origin. So, yeah, what we found is that u of the vector R is actually a function of the magnitude of that distance from the origin, integral f of R, this magnitude function of the force, PR h of R. So that's a simplification. And this is what you guys are going to use to integrate up what I've just given you as a homework problem. This is what you're going to use when you do any number of these central forces that way. Good. I'm still worried about this picture here, but okay. Take a good one in your notes. Just enlarge, make it a bit larger and it should all make sense. Good, okay. Okay, here we are, Newton's law, potential energy. Energy is conserved, and of course the force is the gradient of the potential energy. So that's what I'm going to do next. I'm going to leave this up, we'll erase this development here. And I'll put this as a question. What about F equals minus gradient of u? What about F is minus gradient of u? And we have u of R in that form. Okay. So F equals minus gradient of u equals minus the gradient of this minus integral R. And actually, I guess we have to prime those if we're being accurate about it, R prime, dr prime, because there's the argument. This is some function. Let's just write this. So it's the gradient of this integral. This goes back to that homework problem that I put up there yesterday. This is, I'll give it a different name. Let's just call this phi of R. Okay. And what's the gradient of a function phi of R? Where gradient phi of R is equal to phi prime of R. That's why I assigned that thing on the homework last time. You want to become accustomed to these kind of relations here. And so this was very general. What we have here is this phi prime is just the derivative of this thing in parentheses with respect to R, which is just the integrand evaluated at the upper boundary. So f of R, and then we've got the unit vector. Check. So that works out as well. Force is minus gradient u, there it is, the force, f of R over R, comes up there. Okay, so that works. And so let's write down what we have now. We have a central force, we have a potential energy in its form. I'll do one more step and then we'll gather them all together. Okay, so far we have central force, it has a potential energy, therefore has conservation of energy, the gradient relation works. Next, let's look at angular momentum. Now, this is kind of just being pulled out of the hat, but we remember that the thing exists. It doesn't matter. I can actually just pull it out of the hat and define it and say we're gonna investigate it. So angular momentum, we're going to call it lowercase l with an arrow on it. That's r cross p, but we haven't even discussed linear momentum yet. So it's r cross m r dot. So that's our definition of the angular momentum. It's not the first time we've seen angular momentum. It's a little bit unmotivated right here, but it's very important. We'll see. So let's take its time derivative, dLdt. Its time derivative, right, r dot cross m r dot plus r cross m r. Second derivative. So yeah, these kind of rules hold with vectors and vector products. Product rule, okay. And yeah, here I'm hesitating. Do I tell you guys to prove that as well, or do you just take my word for it? Points to ponder. Yeah. Ideally, we prove everything and anything in this class. We'll put that on hold. Good, so that works. You got a product rule, you're just applying this way. I'm going to do this really thoroughly. R dot cross R dot plus R cross M R. Derivative. One more step. This already we know is already zero. Okay. Because these two vectors are parallel. So that's zero. What about this here? Well, we have R cross, and I'll replace this with its force law, F of R over R. Okay. And for this thing, we can pull the scalar out, so F of R divided by R, and then we have R cross R. Also zero. So the whole thing equals zero, exclamation point. And what do we have here? We have a conserved quantity. So angular momentum is automatically conserved in the central force problem. Angular momentum is conserved. We have another conservation law. So this is conservation of angular momentum. Okay, central force has conservation of angular momentum. All right, now we're going to gather these things together. Gather them together. I will erase the entire board just so we can start a fresh list. I'll put it on the left here. Make it not too big. Before I do the list, in fact, before I do the list, let's do one more discussion of the angular momentum. L equals R cross M R dot. So what does it mean for this to be constant? That means this is a constant vector. By the definition of the cross product, it's perpendicular to both of these vectors, perpendicular to the one, perpendicular to the other. And when these vectors aren't parallel, they span a plane. And you've got position and velocity, therefore, lie in a constant defined plane, which is to say, the motion takes place in a plane when you have a central force. So, having said all that, let's do a little picture and get some, so we've got this vector L, and it's constant, So it's standing perpendicular to, a plane. So L is perpendicular to the plane in which the motion takes place. Plane to which the motion is restricted. The motion is restricted. How about that? Is restricted. Plane to which the motion is restricted. In other words, the motion takes place in a plane, and now we can pull out our plane polar coordinates that we so diligently studied earlier in the semester. So now I'm ready to put the list up of everything that we have seen so far, right? Make clear to yourself that this tells us, because it's constant, that the motion is restricted to a plane. This is a constant vector. Positions and velocities are both perpendicular to this vector, and they span a plane, generally speaking. These two vectors. Okay, so now we can bring in the harvest of this central force problem, formalism, and write it all down. So we now have a differential equation, Newton's law, like this. It has a potential energy so, let's leave the bottom. Energy is conserved, of course. E equals 1/2 m r dot squared plus u of r. And this is the magnitude of this vector r. And angular momentum L equals r cross is also conserved. So this is what we have in our central force problem. And from this last result, is L. In this last result, we can use plane polar coordinates. Wondering what those things were going to be good for. Here it is. We use plane polar coordinates now. Now, what did we have with our plane polar coordinates? Plane polar coordinates. I'll do the little arrow over here. Yeah, r is equal to r cos phi, r sin phi. But we had a more compact notation. That was a vector. We've already done all this work. You may want to go review it. Or dot is equal to r phi dot phi hat r hat dot over phi hat is equal to 0. Remember, these were unit vectors. And yeah, this r hat is also this vector that we've been looking at. This is also the r hat. Okay, we don't need the acceleration here because we already got it back to conservation of energy. So we already have one integral of the motion, so we're not necessarily going to have to work with this, although we'll write it down just for fun, but we'll be able to work with this right here. So, let's get the angular momentum first. L is equal to R cross M R dot. So what do we have here? R hat cross M R B dot B hat. And you guys remember this? X, Y, R hat. P hat was perpendicular. If you cross R hat and phi hat, you can get K hat, namely the one that sticks out of the board. So, good. It's implicitly there, right? We're living in the XY plane, but the K hat vector is coming out right here. So this is immediately M R squared phi dot K hat. R hat cross phi hat is K hat. So that's L vector. K hat's unit vector. L magnitude is M R squared phi dot. So there's a result. I'm going to leave these up here. Okay, so I'll just be working on the right side of the board. So we have found this expression in plane polar coordinates. Now let's do the energy. For the energy, we just need the R dot squared. So R dot squared is equal to one take, just made a mistake. Let's retract some of these statements here, but it's not fatal. In fact, this is going to have to come out right. But here was my mistake. All right, and out there in video land, R dot was R dot R hat plus R dot P hat. Yeah, these things happen. So let's do this. And R cross R dot, we're going to say MR dot, is equal to R hat cross M R dot R hat plus M R B dot E hat. Okay, you see what's going to happen. The cross product R hat cross R hat, they're parallel at 0. That's why the thing vanished. So we're getting the same result back. Sorry about that. We're getting M R squared P dot K hat again because it's from this cross product right there. These two were parallel and it vanished. Okay, so this result is secure and so L is for the record is equal to M R squared P dot K hat. L magnitude is equal to M R squared P dot. Okay, you can erase your notes, but I can't erase this tape because I don't have any editing skills yet. It's just one tape. All right, moving right along. We want to wrap things up shortly. Okay, so we were back to the energy here. You see, this is why I discovered my mistake. So, finally, for the energy, we have R dot squared is equal to R dot R hat plus R dot B hat dotted into itself. E hat. And this is the beauty of these supposedly awkward expressions here. The cross terms vanish. Phi hat dotted into R hat vanishes. And so we're just getting R dot squared plus R squared P dot squared. Multiply it by 1/2 m, and boom, we're in there. So now I'm going to erase this side of the board and put our summary up here. Put our summary up. We've got all of this. And that's why I'm leaving that material up when we get these results. Now, we have 1/2 m r dot squared plus r squared dot squared plus e of r is equal to e, and m r squared e dot is equal to L. So here's what we have. We have this central force problem. You know, we started out over here with these forces, and now what we have is two differential equations. These are both, and we have two first-order differential equations. And these two first-order differential equations allow us to solve for r and for phi, which are our two quantities of the plane polar coordinates with which we can then, you know, express the solutions to the problem at hand. So two first-order coupled differential equations. That's what we brought it to. The motion's restricted to a plane. We have two coupled first-order differential equations for solving all of our central force problems. Good. So this lecture is also about 40 minutes long already. I was intending to keep them a bit shorter because it's important that you write these notes down and really master them. And so if the lectures were a bit shorter, you could watch the video twice at least, really write it down and get some good notes. I consider getting the good notes one of the primary goals of the remainder of the semester for us. Get the good notes and of course learn all these things. And you can rewind, you can stop and fill in anything you didn't know, fill in some words, and you know, we're putting some problems up at the same time as well. Okay, let me write here next time. What we're going to do next time, setting up, I'll just say, the effective potential. And its analysis. So what is the effective potential? Tune in. That's what we'll find out next time. So far we made great progress. This is one of the nice, key, beautiful theories in mechanics, and we're taking it all the way through to the full Kepler problem. We got plenty of time to do it. I'm not worried about that at all. Okay, good. Next time.